él nos va a hablar sobre los retos y desafíos de la integración de los empaques en los semiconductores. Doctor Medina, muy buenos días. Tenemos aquí al director de investigación para que nos dé la bienvenida.
Muy buenos días a todos, bienvenidos. Yo creo que es una excelente oportunidad. Muchísimas gracias, Dr. Joop. This presentation will be in English?
Yes, this presentation will be in
Okay,
English.
so welcome everyone. It's a pleasure for us to have you here, Dr. Joop, and especially with this so interesting topic, package integration challenges. I'm pretty sure it would be very interesting for everyone. So I hope you get the best out of it. So enjoy the session. This is part of our Research and Development Conference series. And thank you very much again, Dr. Joop, for being part of it and participate with us. Thank you, everyone, and enjoy the session.
Gracias, Dr. Medina. Dr. Joop, Dr. Carlos Medina is the research director in all of our campus in the national country.
Mm-hmm. Very good. Well, thank you very much for this very nice introduction, and thanks for inviting me to this talk. And yeah, the topic of the presentation is package integration challenges. And the material that I will be presenting is actually based on a program, the Semiconductor Packaging University program, that I both created and am coordinating in the Netherlands. And it's based on material from different contributors, various contributors. So let me start by package integration challenges. All attention in the media in general goes towards the semiconductor front end. Well, how big companies like Intel and the Samsung squeeze out the last nanometer out of their transistor. So what's so challenging about integration and packaging then? And I hope that in this presentation, I will convince you that there is a shift of these technological challenges from the front end to the back end. So the front end is manufacturing of the wafers, and the back end in general is considered to be everything that's afterwards. So assembly, packaging, testing, and things like that. So, and some of the examples you can see already in these pictures, like stacked die in the use, or sensors with openings and all kinds of fibers. So the talk is roughly separated into three parts, a sort of an introduction, and then I'll take a look at system integration and the effect of system integration on packaging, using two cross sections, you could say, more or less. So from system integration perspective, but also from the trends that are driving the electronic industry. And so we see a lot of overlap in that, but it's another way of looking at it and how you come to the different packaging challenges. So let me start with the basics first. Why do we do packaging at all? And of course, the main part is that it provides a mechanical and chemical protection against the environment. And we will see later on that when we talk about sensors, that we're actually going to violate this more or less. Moreover, it allows us to assemble it on a printed circuit board, for instance, or it enables an electrical connection. It enables a thermal connection in that sense, especially for power packages. And it enables us to standardize the packaging world. Well, assuming that not everybody is familiar with the complete flow, I've here a sort of an overview of a generic packaging and assembly flow, in which you have the pre-assembly, so the wafer has been manufactured in a foundry, let's say TSMC or something like that, or Global Foundry. And so the wafer has been manufactured, and then it enters this generic packaging assembly flow. Yeah, you have to grind it and saw it, singulation they call it. Then you go to the interconnect processing, so you have to attach the die and wire bond it, and this is a generic flow, so wire bonding to have the electrical connection. And then you go to the encapsulation, so somehow you put it in an encapsulated media, and finally you go to final testing and you ship it to your customer. And then there are several ways to classify packages, and this list that you see in front of you is not exhaustive. It's not the only possible list to look at packages, but I have taken these three. You can classify a package by the way how it's inserted on a PCB, for instance. The very classical through-hole devices, which you see on the top right. That's a very classical dual inline through-hole assembly, but also surface mounted. So the other packages that you see are surface mounted. They are not through the hole. And you can have contactless packages, board assembly, I should say. Then another way of looking at packages, or to classify packages, is how they are constructed and what materials are being used. Most of them that we'll know are encapsulated in plastic, but it can also be in ceramic packages, and it can be constructed on the wafer level or by a laminate, as we will see later on. And the third classification way of looking at packages can be, and again, this is not an exhaustive list, but we'll see this later on in the presentation, is how they deal with power, the power dissipation. Do we have low power, like logic, standard logic? Then you do not need any particular measure for your package, and you can just encapsulate it in standard plastic, and that goes up to a few watts. Medium power, a few tens of watts, you already have to take special measures inside your package to get rid of this power. And of course, it gets worse when you go to very high power dissipations. Then you have to add what they call heat slugs to really guarantee that the chips will not overheat. So a little bit more detail here of what I mean by these various classifications is, for instance, this landscape, the package landscape, in which we look at the material and the constructions used. So you have lead frame packages in which the silicon or semiconductor die is first connected to a so-called lead frame, and this lead frame later on will give you the electrical and thermal connection to the die, to the semiconductor. But if you go to very high connectivity, so a lot of these connections, then you have to go to the laminate packages in the middle. So I think very popular ball grid array. So all the microprocessors that we know of make use of these technologies, ball grid arrays, and they can have up to 1,000 or 1,100 or more leads actually. And then the last category is in which the package is actually done on the wafer itself. So the previous two categories, you first singulate the die, so they work on individual dies, and the last category, you actually encapsulate them as a wafer, as a whole, and then later on you singulate them, as they call. Now looking at the way the characterization or classification of packages, how they are mounted on the printed circuit board. Well, on the left again, you see the leaded, what they call the leaded packages, both the dual inline at the bottom as the quad packages at the top there. Then in the middle, we go to leadless packages, and the leadless packages, they were actually demanded for by the smartphone companies, because they can be made much thinner and they take up much less space on the printed circuit board. And then again, we'll encounter the ball grid array on the very right. And then you see a lot of abbreviations. And for the ball grid array, for instance, you can have a thin or a low profile or a fine pitch, and that's where the TLF stands for. So within each package category, you very often, and we will see that later on, you very often also see an evolution in time of how they evolve into thinner and smaller packages in general. And then lastly, again, the list is not exhaustive, but just to give you a flavor of how you can classify packages, standard packages, is looking at the power. You can, for the low power application, you just put them in plastic, to put it bluntly, and that's up to a few watts. But if you go to the right-hand side of this slide, what you see here are typical amplifier ICs, so the things you will encounter in your car radio, for instance. And there the powers can be well, up to tens of watts. And how to dissipate that, then you need a so-called heat slug. And let me see if I can get my laser pointer here. So this is a heat slug, so a metal insert in your package on which the die is connected, and so that you get a very good thermal contact. And also the holes you see here in these packages, and the holes over there, they are there on purpose, because these ICs are typically screwed onto a heatsink inside your equipment. So again, this is looking at the three cross sections or three classifications way for packaging. But as I already explained, there's a lot of evolution going on, even within a single type of package. But if we look at the evolution as a whole, then we started in the 1970s with a dual in package or dual in line ones here. And the problem is that if you have a lot of connections, and they go, I think, up to 64 more or less, standardly 64 connections, that the package will become much, much bigger than the actual silicon die that's inside. So that's not cost effective. That's why they went to the quad packages, in which you're using all four sides of your package. So that's already an advantage. But still, when you go to the thousands of connections, like for a microprocessor, even a quad is not very efficient. And then the next step is the ball grid array, as I explained. But then the thing is that with these packages, that you need what they call redistribution layers. And why? That's in general, if you look at the connectivity of a silicon die, then it's at the periphery, always at the periphery. So if you have your ball grid array, which uses the complete area of your package, then somehow you have to redistribute the connections from the periphery of your chip to the ball that is making the connection somewhere on your area. And that's why these are on so-called laminates and not on lead frames. So here you see a sort of, it's probably not very big on your screen, but here you see how it is redistributed from a single chip to all over the area below the package. And then, of course, when you have to integrate even more than just a single chip, you go to stacked dies, like we've seen at the very first slide in your USB stick. The capacity of your USB stick is increasing because we stack 10 chips on top of each other and connect them somehow. You go to the system in packages, and even further, you go to 3D integration, so stacked dies and multiple dies. And we will see that some examples of that later on. So this is again the evolution of packaging, but also within a certain type of package. And I've taken the QFP package, so the quad package, as it is called. It started out with a simple form factor, of chip area versus area of the package of about 5.5. So that's still not very efficient. And then we went to the BGA, in which the so-called form factor is about roughly 2, so that the package is about twice the area of the actual chip inside. The next step is going to what they call a chip scale packaging, which is even denser. And of course, this is all done not only to integrate more, but also to have some cost down. And then going to even denser and denser systems, you end up with 3D integration and package on package, POP as they call it, package on packaging and 3D integration with through silicon vias, in which you connect one chip to another chip while you put the one on top of the other. So far the introduction more or less, and now we're going to see where all these developments come from and why they are needed. And as I explained, I will use more or less 2 different views on where they come from. First of all, heterogeneous system integration, and I start with a very bold, I think, statement from Professor Zhang from Delft when he was at Intel already in 2003. And he said to these Intel guys that the challenge is no longer in the front end, so in the last squeezing out the last nanometer, but the real challenge is in system integration. So, well, I don't know what happened, but he's still alive. And so heterogeneous system integration, what is meant by heterogeneous system integration? Well, it is the combination of various technologies and various functional devices in one system. So system integration, we're not at the package level yet, and I will come to that right away. But in principle, on the highest level, this is heterogeneous system integration. And if you look at it from a functional point of view, then this integration controls most of the performance, about 70% of the total cost, and about 90% of the size and the reliability. So system integration is very important for the final end product. And on the highest level of looking at system integration, and as I said, I'm not yet at the package level. You see these different systems. You have the sensors, the actuators, the radios, as they call it, and there are for the network and media and data. In general, a system like this has various radios. For instance, one for Wi-Fi, one from Bluetooth, one for GSM, for instance. Then ICs, which can also be multiple ICs, memories, data processing, and other stuff, and multiple controllers, drivers, power management, and of course passive. So this is heterogeneous system integration at the highest level. Then one level down, you get to the architecture, to the PCB. And also on the printed circuit board, you see what's happening with heterogeneous integration, because already here on this printed circuit board from a mobile phone, you see a lot of different chips with different functions, and also, by the way, from a lot of different manufacturers. So this is the system architecture. But now we go to the package level, you could say, and looking at how these different levels of integration work out for different markets. So how the markets have their requirements for system integration, and then, of course, I will relate that to what it means for packaging. In general, we distinguish 3 levels of integration in this respect on the assembly and packaging: the wafer level, the package level, and the substrate level. The wafer level, of course, starts right away after wafer manufacturing. So it can be what they call wafer to wafer or chip to wafer integration. And the most important challenge there, you must imagine that if you, of course, flip one wafer on top of another wafer, that you must really be very careful about the alignment of the various devices, which is a little bit easier, but still not very easy when you do chip-to-wafer integration there. Then on the package level, so now the wafer level, you do the system integration before you actually singulated the die, before you separated the individual chips. On the package and the substrate level, you first separate the individual chips, and then you're going to either combine them in a package or on a substrate. So in a package, we already seen that, for instance, if you use stacked ICs, then that's all using several ICs, for instance, memory ICs, in one single package. And there, one of the challenging factors is, of course, how to connect them, especially if you use, for instance, wire bonding. Then it can be, well, quite a substantial structure with all kinds of wires, which, of course, are not allowed to touch each other. Of course, if you're going to put a lot of these systems in a single package, also, the thermal dissipation is becoming a problem. And then on the substrate level, integration, heterogeneous integration, we're actually combining, you could say, different packages in one, and a lot of different technologies and a lot of different devices there. So taking a little bit more detailed look on wafer level integration. So there, as I said, it can be chip to wafer or wafer on wafer integration. And the challenge there, as I said, is for a large part how to align the two wafers with respect to each other, because the connections are, well, relatively large, maybe tens of microns, but you still have to have a good overlap of that. And of course, heat dissipation is also one of the challenging factors there. The wafer level integration is also used on wafer integration is also very often used when they combine electronic devices with optical devices, because there you need, for the very high frequencies, you need a very intimate contact between the two. And then I take together the package and the substrate level multifunctional SiP, and you see here a very complex substrate level assembly, actually, in which we have combined a multitude of materials, but also devices. We have a biosensor here. This is, of course, an extreme case, but there are, well, through glass capacitors, we have photodetectors, lasers. So it's a combination of different devices, and therefore also different materials and different technologies in one package. And in those cases. So if we now look at what are the trends and what are the markets that require this very intimate integration, and what challenges does it pose on packaging? Well, energy and mobility, and with energy and mobility market, you should think of autonomous driving. That's intelligent, you could say, and on the other end, the power, solid state technology, and electrical vehicles, and the combination of these two. Though energy and mobility, for a large part, is combined in the electrical vehicle, especially when it's autonomous. And so there you will encounter very high powers, the large currents, a lot of dissipation, harsh environments, and also high reliability, because you can imagine we all drive a car, I think, and we don't want anything to fail there. And especially if you think of autonomous driving, that's even more important. So what are the trends there in integration, what integration is concerned? Well, we started with silicon power devices. We know them best but they're not the best choice in this case. So what we see emerging now is what they call wide bandgap semiconductors, and those are semiconductors like gallium nitride and silicon carbide. They can work at much higher temperatures, and they can dissipate much more power. So in the midterm, you will see that the power is done with these wide bandgap semiconductors, while the control electronics is still silicon based. And then on the long term, everything will be in the wide bandgap semiconductor electronic systems. If you look at it from a packaging perspective, what this means for the packaging, of course, apart from dissipating these enormous amounts of heat, another thing is that these wide bandgap semiconductors, they are very brittle. Silicon, in a sense, you can actually, silicon is a very forgiving substance, a material in that sense. As long as you don't scratch it, then you can push on it and it will not break. But these gallium nitride and silicon carbide, they're very brittle, so that means that you have to reconsider your assembly and packaging flow for these materials. So that's what it means for packaging and assembly. And then maybe a market you're less familiar with, or because health and environment. Again, that's not huge at the moment, but what is characteristics of this market is that it's multidisciplinary. That also when you're developing a package, you will probably have to work with a biochemist and a chemist and medical people. And moreover, especially when it's implanted in the body, the materials that you will use for the package must be biocompatible. They must be compatible with your body tissue. And very often what you will see is that it involves some sort of a sensor in combination with fluids, for instance, blood or saliva and things like that. And while normally a package is there to protect the chip from the environment, in this case, you inevitably need some sort of a hole in your package, because otherwise your sensor will not work. And then connectivity market and Internet of Things, well, that all is developing around data and data rates, the higher data rates, higher frequencies and higher data rates. And also there we see wide bandgap materials emerging like gallium and nitride. But if you go to the higher frequencies, and we'll see that later on in the talk, that has a large impact on, especially in the millimeter wave, on your package. But what I wanted to point out, especially here, is photonic integration, because in these connectivity, high data rates, a lot of the data centers, everything is transported by fibers, by glass fibers. So what you see there very often is that the data rates are determined not so much by the electronics, but by the photonics in combination with electronics, because electronics delivers the driver power for the photonics. And then photonics packaging as a particular topic here, for instance, for LiDAR in automotive, but also for 5 and 6G telecommunication. The photonics packaging is a world on its own. In general, of course, you have the challenges which you're already facing with electronic packaging, but added to that, you have the challenges of having to interconnect also glass fibers to this. And to give you a little bit of an idea why that's so challenging, the alignment accuracy in general for an electronic connection is about 10 micron. The accuracy for aligning an optical element is in general less than 100 nanometers. So it's at least 100 times more. You have to be 100 times more accurate in this case, and then all in the same package. Moreover, in general, these photonic materials are very temperature sensitive. So while a silicon chip, a normal silicon chip is specified to operate between, let's say, -25 to plus 125 degrees. The operating range of a photonic chip in general is much, much less, can be even a few degrees centigrade. So you have to provide some sort of temperature stabilization in your package. And that's why I added also cost here. In general, about 90% of the cost of a photonic chip is in assembly and packaging. So that's a big challenge for the industry to actually cost down the packaging of electronic packages and photonic packages. And now, as I announced already, I'm going to use a little bit different approach to look at the challenges of packaging and coming from the electronic industry. As you can see here, you will recognize already the markets that I presented to you: automotive, mobile, telecommunication, and some more. And what is driving eventually a lot of this industry, and that is what they call the road to augmented intelligence. You could say the robotic vehicle is already one expression of augmented intelligence in our world. And the strange thing, and that's also why the Gucci Chang made this statement at Intel. What you see here is on the top, you see in time the evolution of the front end of these advanced nodes, of the squeezing out the last nanometer of your transistor, as I called it. And then at the bottom, we compare it with how the evolution of the back end, so how the connection and the packaging has evolved in time. And while in the front end, in the advanced nodes, we are talking on a nanometer scale, you immediately see that when we're going to connect these, we're immediately on the micrometer scales, if not 100 to 10 of micrometers. So that the whole back end, as they call it, the whole advanced packaging and evolution is clearly lagging behind what has happened in the front end. And that's why a lot of companies, as we will see later on, and also the companies which you see in the top there, companies like TSMC and Samsung and Intel and Global Foundries, but especially the top three, that these companies are investing hundreds of millions of dollars in advanced packaging now. So let's look at the different megatrends. For instance, automotive, we've already seen it a little bit. What's happening there? Well, also, this will not be coming as a surprise to you. We see on the one hand electrification, the electric car, and autonomy, so the autonomous car. And both require different electronics and also have different impacts on packaging and system integration, especially in packaging. There are two strategies, you could say, a revolutionary strategy, which is called the ADAS vehicle. So they add the existing brands of automobiles. They add more and more features to assist the driver. It's a driver-assisted vehicle, advanced driver-assisted vehicle. So in time, you go up towards the autonomous vehicle. And another brand, and then you can think of a brand like Tesla, they more or less came up with a sort of a robotic vehicle in one go. And because of course, they had more or less the advantage that they were not already producing vehicles in that sense. But to make that possible, you need an awful lot of electronics in the car. And this gives you an impression of what you need in terms of electronics to come to this robotic or autonomous vehicle. And all kinds of different ranges, different technologies, and of course, all coming with different requirements for a package. And it is the whole range from sensors. The radar is now LiDAR. We have ultrasound, and it requires MEMS and sensors, power devices, but also a lot of computing units. If you, especially for LiDAR, for instance, if you go to advanced LiDAR systems, then they need very, very advanced computing units, because they have very little time between one pulse and another pulse to evaluate the signal that is coming back. So far electronics, and of course, if we stay a little bit with the car, as I explained, so one slide back again, looking at packaging. Here, sensors are, of course, a big issue, and we'll come to that later when we go to high frequencies, but also the high power devices, how to dissipate these power, and then working with these very brittle materials like gallium nitride and silicon carbide. So now to telecommunication. We all have our smartphone, of course, and I haven't looked at Panama on this. I see Panama, but in this slide, which is from 2019, so that's already some time ago. This gives you an impression of the so-called 5G rollout and pre-release. And so that's already in 2019, quite a few countries were working on the rollout of 5G. But what a lot of people do not know from 5G is what was actually rolled out was more 4G plus than 5G, because the base frequency, the baseband frequency, is still at 2.4 gigahertz, what also 4G is on. The real 5G, so to speak, the real high bandwidth network is actually going to work on 28 to 39 gigahertz. And that means millimeter waves. And if we now look at the packaging and system in package, well, for anybody that has some feeling for antennas and how they interact, then millimeter waves is the scale of a chip, of a package. So that means that before you know it, whatever you do in the package is going to interact with the signal that you're trying to transmit or trying to receive, but in general trying to receive. And the companies, the various companies that are active in this, in the mobile area, like Apple, Samsung, Huawei, Oppo, Vivo, Xiaomi, they approach it differently. What integration is concerned. So you see here a microphotograph of a very complicated system in package. So they either the high-end branches, but also the high-end phones for Apple and Samsung, they have a very large integration scale in the package, as you can see it. This is an RF system in package. While other companies like Xiaomi and Oppo and Vivo, they deal with it more on the printed circuit board. So they still have a lot of separate, discrete devices. But you see this trend in time for the front-end module. So the integration here, again in time, expressed in this slide. So we come from discrete packages with discrete elements, and then that was 2G, and then we get into the 3D and 4G domain, in which you see more and more system in packages. Then for 5G, we go this one and sub 6 gigahertz. Which is a sort of an intermediate stage for 5G. You go to, for instance, a double-sided system in packages to increase the integration rate. But if you go, as I already mentioned, to the real 5G, I would call it, so there's the millimeter wave, then you need all kinds of tricks, because as I already said, you get interference, your antenna gets very small, and also you have to integrate your antenna in your chip itself. So somehow you will have to make a connection through the package to the antenna, which is on top of your chip, for instance. Moreover, you have to shield, as it's AMI shielding, you also have to shield the underlying chips from the signal that you're actually trying to transmit. So if you look at what they call the toolbox for this, then you have various things you can do. You have to do shielding. You have to do double-sided assembly for higher integration densities, but also go to low-loss materials. And maybe we better go to the next slide for that I'm concerned, because you also have to integrate a lot of passives. There is a lot of filtering going on in the mobile phones, and there can be both bulk acoustic waves as surface acoustic wave filters, and they all have to be integrated very closely, especially with these millimeter waves running in your smartphone. They have to be integrated very closely in your one package. And that means that, as I already mentioned, that you have to integrate the antenna, and you have to integrate strip lines for connectivity, because millimeter waves you cannot just do it via wire, and you have to shield other chips from the signal that you actually want to transmit. So it's very complicated packaging technology that is not really, there is no holy grail yet in this case. And one of the other complications, for instance, here you see these blue squares there, they're all antennas, because the next stage in 5G telecommunication requires more than one antenna to actually work. And then the shielding, there are two types of shielding. As I said, we are integrating with 5G a lot of different components, both passive and active components, into one package, and that's necessary. Otherwise, with these millimeter waves, it will not work. But on the other hand, you have to shield the one chip maybe for the signal of another, and that can be conformal, as you see here. So in fact, you encapsulate, you could say, several chips by a metal shield, but it can also be compartmental, so one chip by chip type of shielding. And finally, the last, you could say, mega trend is, of course, computing and data centers. And with computing and data centers, you basically have to think of everything that has to do with the Googles and the Netflix and things like that. And there's a lot of optical communication going on, as I already mentioned. And so there, the integration and packaging of optical chips is becoming very important. And the various players in this field, which we already encountered a little bit, the TSMCs and the Intels and the Samsungs, they are investing many millions of dollars in developing the various solutions for this heterogeneous integration, especially for the 3D type of integration. And you see also different solutions here. So this is a branch that uses through silicon via. So you make connection from one chip to another chip by actually drilling holes and through a chip and filling them up with the metal to make the connection. There are also without through silicon vias that use a substrate approach. There is a 3D stacked memory approach, SoC approach. You see that a lot of companies are very active in this, and also that it's quite a challenging area that we are working in. So in summary, I talked a lot about heterogeneous system integration and why it's so important and what its impact is on packaging and heterogeneous packaging. So heterogeneous system integration, is no longer, we can no longer do without it. We're integrating a lot of stuff in the same system. It's also the way you do it is also very important because it determines the performance, it determines the cost, and it determines the reliability, size and reliability. That there are 3 levels of system integration, can be at wafer, package and substrate level. And there we think of a system in package, hybrid bonding, through silicon vias and nanostructures, 3D printing. And there are various markets that are driving this heterogeneous system integration, mainly, but not exclusively, but mainly, and the biggest one are automotive, via the electrification and autonomous vehicles with their sensors and power devices, telecommunication, and 5G and 6G later on. People are already working on 6G with the integration of passives, the integration of antennas and shielding and strip lines, all in one system and in one package. And then the high performance computing and data management, in which you can think of again with the through silicon interconnect, but also hybrid bonding and 3D stacked memories. And with that, I'll finish my talk. It's open for questions, and I have some background reference for the people that want to look at it.
Excellent presentation, Joop. Thank you very much. And now we open the opportunity to ask questions. You can open your microphone and ask the question to Dr. Joop.
Hi, this is Delida. Thank you so much. It was really, really eye-opening, especially the the gap between the front end and the back end. And my question to you: do you see any of the companies working on which are the vertical companies that have the whole thing, working on the front end to accommodate the back end? For example, pre-drilling the holes in the chip, in the substrate, the silicon substrate, so that it will be easier at the end to do the integration and that kind of stuff. And if that is a trend, and if that is a trend, then how it's going to work out for the fabless companies, which are the most interested in communication?
Yeah, well, that it is definitely a trend, I would say. Yeah. So although in one of my last slide, I showed that not everybody is going that way. So there are other solutions. It's not, as I mentioned, it's not the holy grail through silicon vias. You can also, through polymer vias. There are other ways to more or less reach the same result. But you could say the obvious factories which have a lot of experience in producing silicon in that sense, they go the way of through silicon vias, while the others that have less volume or less experience, they in generally take another road. That's what I would say. But the big ones at TSMC, Intel, Samsung, they are all on the through silicon vias. But again, that's not the end of the world. It doesn't mean that the fabless companies cannot access it. There are other ways. Did that answer your question? Yeah.
Yeah. Yes. Thank you. And I'm not sure this is a follow-up, but it's not really a follow-up question. It's a different question.
Well, the rare earth war is impacting development of new chip. Well, that's a good question in that sense. I do not think it will really impact assembly and packaging, but there are, when you look back, when at the start of silicon production, of the IC production, I should say, I think we only used 5 elements or so from the periodic table. Silicon, of course, and then some boron and arsenic, and some other stuff, but that maybe 5. Oh yeah, aluminum, of course, to make the connection. I believe that we are now in the 50 elements or so. For all kinds of exotic, the gate oxide in the CMOS is a strange mixture of all kinds of elements. We use tungsten, okay. Anyway, so yeah, we do use a lot of rare earth elements, and that's also one of the reasons why in the different continents, also in, I can only, well, I know most for Europe, of course, but I know that not so long ago in Scandinavia, it was announced that they had found a lot of these minerals, and there was a big fuss at that moment in the European community how to explore and exploit these rare earth minerals to become less dependent on on other countries. We all know the countries we are talking about, I think, without really mentioning them. But so I don't think really that there's not a real lack of these elements. Some of these so-called rare earth elements are quite abundant, to be honest, but it's more a geopolitical game. And yeah, what you often see is that the various countries and conglomerates of countries certainly start to look into it. If it becomes difficult, then the semiconductor industry is a very resilient industry. We have been saying that Moore's law will end for decades, and it still goes on. So somehow we'll find a solution, I would say.
Okay. Yeah. Any other question?
Yeah. Do you see any for lead frames, for lead frame packaging, there is still business there, or that's gonna go for chip scale?
Also there, I would say that I said that the semiconductor industry is very resilient, but it's also very conservative in a certain sense. Everything that and you wouldn't say so after this presentation, but of course I wanted to talk about the challenges. But if you look at the baseline, for instance, 80% of the chips is still wire bonded to do the connection. So that's on the lead frame. So the bulk of the only change that this industry, this wire bonding, has undergone is that we went from gold wires to copper wires, and that has already been a major impact on the. So now I would say that the lead frame is still with us for many years. So, and of course, again, what I presented was for a large part the challenges. So that's all in the very advanced packaging. But so with substrate and with redistribution layers and laminates and 3D integration, but the bulk is still lead frame. Does that answer your question? Yeah.
Yes, thank you. That's more or less what I wanted to drive. It's encouraging.
Yeah. Is there any other question from the people?
One more question, and this is kind of like shooting in the sky. The only way that Moore's law can continue to be applied is that we go to quantum computing. Is that something that you see in the future, or you see a possibility? Because we're at the 1 nanometer, we're almost there.
Yeah. Well, it has two answers. For me, at least, it has two answers. Depends on how you define Moore's law. If you and that's not. But with that I mean that if you go back to the original Moore's law, he was not talking about dimensions. He talked about the number of transistors on a chip. It was translated in dimensions because that's the way to get more transistors on a chip. But
Right,
Moore's law principally just talks about density. And now there is one branch of people in the industry that say, if you look at the chip today, the density of transistors itself can still be increased without decreasing the dimensions. So if you look at it that way, so they say there's a lot of empty space between transistors on a chip. That's what they say. So if you interpreted Moore's law in that way, okay, then we can still go on. If you look at it from the dimensional point of view, yeah, then I think the final stage can only be quantum dot type of structures, but also there, yeah, below 1 nanometer, no, not really. So I really think that the real continuation in the development will be more in increasing the density, and so not so much the dimensions, decreasing the dimensions, and also functionality. And a lot of talk has been going on, of course, in 3D integration, also for decades, but especially for computational things, then power is a big issue, and even with the packages, the advanced packages that we discussed, it's still an issue, because if one CPU already dissipates 100 watts and you put 3 on top of them, it's not going to help.
Is heat dissipation always going to be passive?
The question here is if you think that heat dissipation is always going to be passive.
You mean with heat heat fins and things like that, and heat slugs, and depends on, if you look at photonics, for instance, it's already not passive. But as I explained in photonics, the temperature range for instance, an indium phosphide chip is just a few degrees, because the photonic signal is very sensitive to temperature changes. So nearly all photonic chips are temperature stabilized. Do I foresee that for silicon chips? Well, there's no. They can already do it. So it's not widely. No, it's not widely done in so. And while in the data centers you already see forced cooling and water cooling. So yeah, there are even chips being made, or packages, I should say, packages being made with actually holes through the holes, so that the water cooling and the cooling the cooling liquid can be very close to the chip, to the die. But that's, for the moment, that's so expensive, and it will not be, definitely not be mainstream now.
Okay. Thank you.
You're welcome.
Okay, I have no words to thank you, Dr. Joop, for sharing your knowledge, your time, your experience, your wisdom with us.
Enthusiasm.
Thank you so
Don't
much.
forget enthusiasm. Yeah.
Yes,
It has been a pleasure.
Enthusiasm.
It has been a pleasure, and okay. I wish you all a very pleasant day.
Yeah. Okay, and it was very, 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 very interesting conference. Fabulous. I'm
Thank
going
you.
to watch the video again and again.
Okay. Wow. Yeah.
Yeah. We'll send a test to everybody.
Okay, great. I'll be famous. I'll be famous.
Yeah.
Thank you very much again, Dr. Joop, for being part
Okay.
of this series and exchange all your wisdom with us. Thank you.
Okay, you're very welcome. You're very welcome. Okay, wish you all a pleasant day.
Yes, gracias
Goodbye.
también a
You too.
gracias a todos los que participaron y han tomado de su tiempo para acompañarnos. Esperamos que la información brindada el día de hoy sea provecho para todos y nos acompañen en los ciclos de conferencia de la Dirección de Investigación. Gracias.
Muchas gracias, Zoila. Excelente.
Okay.
Gracias a usted.
Gracias a todos y espero que lo hayan disfrutado. Saludos.
Saludos.
Saludos.